Alright guys, we got our study guide for the semester exam, Unit 1. I'll go through it here with you. Remember, this has been designed for the person who isn't planning on using your formula sheet, so every once in a while you'll have to produce a formula, and then if you know all these formulas, then you should be ready for the exam. So we'll start up here with the definitions. Physics is simple. It's the study of matter and energy. So that's one we've had all year long. There shouldn't be any surprises there about that one. It's a piece of cake. Study of matter and energy physics. Measurement is a quantity plus a unit. So we have to have some quantity and a unit. Accuracy, one-word definition of error, or how close you are to the actual answer. Precision, one-word definition of uncertainty, or how often you get the same answer. These two things show up down here in percent uncertainty and error. Percent uncertainty doesn't relate at all to what the correct answer is. It's just how far apart your answers are, where percent error is relating it to the correct answer. Parallax is something you want to avoid in lab. It's when you view a measurement at an angle. So when you view a measurement at an angle. And then finally, sig figs. These are the precise numbers, or how far out the tool works. The more money you pay for the tool, the further out it's going to read, as a general rule. Alright, so let's do these two equations here. Percent uncertainty is the deviation, we call it the plus or minus number, over the average. And percent error would be the actual, that's what you get, theoretical, what you look up on the computer in your book, divided by theoretical times 100. And plus or minus doesn't mean anything here. It's just how far away you were. If the number's higher, you get a positive percent error. If the number's lower, you get a negative percent error. Then we move into the three fundamental quantities and units. So remember, these are on the poster in the room. You never have to memorize these. They're always there. Length, mass, and time. Everything that we've studied so far this first semester is made up of these three things. The units would be meter, kilogram, and second. We can put those together in a number of different ways, which we'll see down here in the derived quantities. But these are the fundamentals, the building blocks. Density is mass over volume, another equation you need to know. Prefixes, you can always look these up on your calculator, but you should know them. E negative 9, E negative 6, E negative 3, E negative 2, E to the third, E to the sixth. This might be something you might want to put on your formula sheet just to save time. Of course, you can always get to it from your calculator, but really you should just know them at this point. Underline your significant digits. Remember the right rule. Zeros on the right side of the decimal on the right side of a whole number are considered significant or all right. So these 3 would be significant, these 4 would be significant. Just 1 here, these are just placeholders, there's no decimal, so it's just a whole number in that one. Only 4 here, this 0 and this 0 are placeholders. And finally in this one, zeros on the right side of a number on the right side of a decimal are significant, so we only get 2. So you just want to remember the right rule, and you pretty much have it. Graphing. So for graphing, we have 3 different relationships. We have linear, quad, and inverse. We can define them with what their y equals. So all of them begin with y equals. Linear, y equals mx plus b, straight from algebra, right? Y equals ax squared plus bx plus c. That's how you do quad. Inverse, y equals a over x. You need to know these before you can start to work numbers. So now that I'm giving you a series of numbers, a y and an x, the x is 1, 2, 3, and 4 seconds, but the velocity is changing, therefore, we're accelerating. If we go to graph this, we just do a simple plot. The x and y's don't have to equal each other. So maybe I say, like, we do a scale of 10, 20, 30, 40, 50, 60. And over here, maybe I do 1, 2, 3, 4. And when I plot these things, I plot it in such a way that I get an exponential relationship. Just a minute, it's hard to talk and plot. And we we have 4 and 64. Therefore, we go on up. We get this, not a straight line, but a curve, and that's how we know it's quadratic or exponential. So the relationship would be quad. Now the hard part is doing the y equals. If you see that it crosses the origin, it's just actually y equals ax squared. You don't have to worry about the b and the c term. And so just pick one of these things, like when y is 4 and x is 1, what does a have to be? And then you can use algebra to solve for a, and you realize that it has to be 4. So y equals 4ax squared would be my relationship. Or 4x squared, sorry. So the units would be, we got to go back up here and look at our data table. The y was meters per second, and the x was seconds. So rise over run, that slope, would be meter per second over second, which is also known as meters per second squared, which represents the quantity acceleration. So if I found the slope, for example, at time 3, that slope would tell me the acceleration at time 3. If I found my slope at time 2, that would tell me my acceleration at time 2. Notice that as it accelerates, the speed picks up, and that's why the slope is steeper at time 3. Now I would also like to remind you once again, you can always plug these things into our calculator underneath SciTools, and if we go to Data Graph Wizard, you can kind of go through and plug in data like I have here, and then it will allow you to create the graph in that way as well, and it will tell you the y equals. We did that in class, but you know, I don't know if you really need to or not, but just to let you know, that's just another tool in your toolbox that you can use. Dimensional analysis. So you know, we haven't done this a whole lot. It's not like in chemistry where you're doing it the entire time. But we're always having to convert back to things like kilograms, so it's a good thing to know. A lot of you can do this in your head, which is fine because all you have to do... What's that, Reese? Okay, just a minute, alright? So we go through here and set up the dimensional analysis. Alright, that's a little messy. So we go milligrams to grams, grams, 1,000, 1 and 1,000. So basically we have to move the decimal over 6 places to the left, and so we get 2e negative 4, or 0.0002. For this one, same kind of deal. Now we have derived centimeters per second to kilometers per hour. So I'd say 250 centimeters per 1 second. So I'm going to go centimeters to meters, and then meters to kilometers. If I stopped right here, I would be in kilometer per second. That's not where I really want to be. I want to be per hour. And if you can remember way back earlier in the year, I told you this might be something you might want to use as a time saver. 3,600 seconds in an hour, 1,000 meters in a kilometer, 100 centimeters in a meter. And basically we're going to need to divide by, or move the decimal over 5 places to the left, and then multiply by 3,600. And when you do that in your calculator, what you're going to end up with is 9 kilometers per hour. And you can check it for yourself. Just one time, maybe it might be good for me to plug it in here. So we'll say 250 divided by 100 divided by 1,000 times 3,600. Remember, everything on the bottom divides and the top multiplies, and you get 9. So everything on top multiplies, everything on the bottom divides. We're just working with fractions here, equivalencies, things that equal 1. We go on to the next one. This is a little bit different because we're talking about volume, and remember, volume can be tricky. So we can say 5,000 centimeters cubed, and we can use the relationship centimeter cubed to milliliter, and then we can go milliliter to liter. This is just something I expect you to know, that these are equivalencies. And there's 1,000 milliliters in a liter. So basically, you know, we're dividing by 1,000 and we get 5 liters. Now we're down to 100 years. How many seconds is that? So we'll say 100 year. This is a great opportunity to remind you about another thing you have available to you, which is under SciTools again. You got your unit converter. So if you want to use this, this is acceptable, right? Maybe you don't learn the most about dimensional analysis, but you know, this gets the job done. We can go years to seconds, but remember, it always gives us 2 in scientific notation, so the answer isn't 3.15. It's 3.15, and then we got to tack 9 zeros after the 3. So we'd say 3.15 e to the 9, which is an incredibly large number, but there's a lot of seconds in 100 years. Then we have density. Density is tricky again. Go through this one time, the setup. This is one that wouldn't be in SciTools, so it forces you to really know what you're doing with dimensional analysis. Centimeters to meters cubed. This is the tricky one. This one's pretty simple. 1,000 grams and a kilogram, but over here we say who's bigger, meters bigger. Always ask yourself the question, who's bigger? That helps out a lot. We're going to have 100 times 100 times 100. Another way to say that is 1e to the 6th. So we end up just kind of getting 14 times 1,000 or 14,000, which is a big number, but it's in that particular unit, kilogram per meter cubed. Finally, for our derived units, we have velocity, which is meters per second. We have acceleration, which is meters per second squared. Remember, it's the rate of change of velocity. We have density, which is kilograms per meters cubed, mass over volume. Of course, there'd be other things like gram per centimeter cubed, but if we're using the fundamentals, that works the best. Volume, meters cubed, area, meters squared, force. We start by using the building blocks, and we get something that looks like that, but it has an equivalency of a Newton. And momentum, which we really haven't talked about a whole lot, but I'm still holding you responsible to, would be mass times velocity or kilogram times meter per second. Another way to say that would be a Newton times second, which we haven't even talked about yet because that's impulse. And impulse and momentum are almost the same thing. Anyway, here's our units. Dimensional analysis, prefixes, what would you want to write down on the back of your formula sheet? Well, I would write down my units. I mean, why not? I also write down the definitions, right? All three relationships and what they look like. Maybe little pictures of graphs. Dimensional analysis, maybe you want to write down some equivalencies that are hard to remember, like how many meters, 1 meter cubed equals how many centimeters cubed. That seems to come back up again and again. Maybe some examples of sig figs. Maybe some prefixes here, especially if you don't know them. Some of your equations that may not be on the front, like percent uncertainty or something like that. More definitions, and then I think density is on the front of your formula sheet. All right, in a minute here I'll work on the next one, and we'll keep this party rolling.